Good morning, everyone, and welcome to the inaugural Symposium on the Foundations of Responsible Computing. I'm Cynthia Dwork. This was a time of moral and desperate sorrow, even before the advent of the coronavirus. The shootings of Ahmaud Arbery on February 23rd, of Breonna Taylor in her own Louisville home, and the asphyxiation of George Floyd in Minneapolis on May 25th. But like Trevor Noah, I keep coming back to Amy Cooper's Memorial Day weaponizing of racism in Central Park. Her absolute certainty that if she lied and falsely claimed an African-American man was threatening her life, she would be believed. I've been thinking about Amy Cooper's attempt to control Christian Cooper by threatening just such a lie. And I'm thinking of the role of technology, the videos of the Arbery and Floyd killings, and of Amy Cooper, whose patent weaponizing of structural racism was exposed. The phones recorded racism, and these recordings have convulsed the country and beyond. But can the phone learn to recognize racism? And I'm thinking about contact tracing schemes originally designed for fighting the pandemic being subverted to track participation of the outraged and of the outrageous in the demonstrations. And I'm thinking of the coroner's report, the combined effects of Mr. Floyd being restrained by the police, his underlying health conditions, and any potential intoxicants in his system likely contributed to his death, issued before the toxicology report was received. His underlying health conditions being blamed for his death at the same time that obesity has surfaced as an explanation for the increased risk among African Americans of severe complications from the coronavirus, of 49.6% versus 42.2% obesity rate, somehow enlisted to explain a 240 to 700% increase in fatalities. And I keep coming back to Dorothy Roberts' admonition that structural racism, not race, is the risk technological designs should engage to help us envision an equitable future that doesn't replicate the past. Against this backdrop, the need for this symposium is thrown into high relief. It is the belief of the founders and the steering committee that theoretical computer science can successfully be brought to bear on problems of great societal import. Theoretical computer scientists can and should engage in these endeavors, and further should anticipate problems of this nature that will arrive in the context of new technologies. And it's our belief that strong contributions along these lines must be defined to be professional success, which requires fostering a community in which such work can flourish. For these reasons, Omer Reingold and I have co-founded the Symposium on Foundations of Responsible Computing. Omer?
Thank you, Cynthia. So I'd like to add that we are incredibly moved at this moment of creation that we are all witnessing. Only a year ago, FORC, with many other tentative names, was only an abstract idea. It was only a realization that a community within CS theory that studies the societal impact of computations is in growing need of a scientific home, a venue that would accommodate its unique rhythm and sensibilities. We were only able to announce this new conference rather last minute, and yet we already have, in the first meeting of FORC, a rich and exciting program exceeding even our most optimistic expectations, and more than 800 registered participants. Indeed, it is clear that the void we have observed is real, and FORC is here to fill it. We hope and believe that FORC would help nourish this community and make it even better positioned to continue to a highly multidisciplinary, to contribute to a multidisciplinary discourse and collaborations that the area requires and to which we are all fully committed. We want to thank Harvard Center of Mathematical Sciences and applications for hosting this event and funding the open access proceedings. CMSA not only immediately agreed to host FORC 2020, but was very flexible, and in addition to their support this year, will also be hosting FORC 2021, hopefully as a physical meeting. And I can announce that we have secured funding to support FORC for a few additional years, so we are off to a great start in this respect. I'd like to thank the rest of the steering committee that were invaluable in all the decisions needed for this rapid forming of a new symposium. We are grateful to the PC chair, Aaron Roth, and the inaugural PC for a wonderful work at the face of unusual conditions. This was a first in many ways, not only being the first time we're doing FORC. And most importantly, we would like to thank the authors and audience, without which there is no FORC. And with that, I'll give the floor to Aaron.
All right, thank you, Omer. I don't have much to add except to say thank you to everybody involved. You know, this conference was organized in much more trying times than we had imagined when we started out. There was a global pandemic just around the time when reviewers would, when the PC would really have been buckling down, and they all went above and beyond to put together what really is a terrific program. The reason we were able to do this is because everyone involved, from the steering committee to the program committee to the invited speakers, really, I think, believe in the importance of the work that we're all talking about, and I'm fortunate to have been involved in such a wonderful community. We've got a terrific program for you today. Hopefully, you've all looked at the program session. We're going to start with a keynote talk by Adrian Weller in just a minute, and then we're going to have a contributed session on privacy chaired by Adam Smith. After that, we're going to have, for anyone who wants to participate, virtual discussion and networking sessions during lunch. For that, we're all going to log off of this Zoom webinar and log in to a Zoom meeting that you should have received in your email over the weekend. And then we'll come back to this Zoom webinar at 1:30 for Ricky's keynote and another contributed session. So with that, let me give the floor to Suresh to introduce our first keynote speaker.
Thanks, Aaron, Cynthia, and Omer. And this is it's an interesting time to be talking about these issues, as Cynthia, as you mentioned. But I'm glad we're here, and I'm glad we could do this, and I'm honored to be able to participate in this. So it's my pleasure to introduce our first keynote speaker of today. Adrian Weller is a principal research fellow in machine learning at the University of Cambridge, and has been working in this area of responsible computing for a long time now. Adrian is also the program director for AI at the Turing Institute. It's a wonderful institute based in London, that's the National Institute for Data Science and AI, which you've probably heard of. He's a Turing fellow there, leading work on safe and ethical AI. He has a number of other hats that he wears, so many that makes me feel tired just looking at all the wonderful things he does. He's a research fellow at the Leverhulme Center for the Future of Intelligence. He's a David McKay Newton Research Fellow at Darwin College. He's an advisor to the Center for Science and Policy, which I think is another interesting sort of angle, another interesting role that theoretical computer scientists get to play now. And the Center for the Study of Existential Risk. He's also serves on the boards of many organizations, many of which and including a member of the UNESCO Ad Hoc Expert Group on the Ethics of AI, and many others as well. Without further ado, I welcome Adrian, and looking forward to your talk.
Thanks so much, Suresh. Let me just try to make sure I can share my screen properly. Can people see my first slide? You can hear me okay?
Yes, it sounds good, and it seems good, yeah.
Fantastic, thank you. It's a great honor to be the first speaker here for the first FORC. I'm very excited about it. In fact, I realized that I'm the first FORC talk. I thought I would get that out of the way. And I particularly want to thank Aaron Roth for doing a wonderful job as PC, organizing a terrific program at a difficult time. And I also want to thank Cynthia and Omer particularly for co-chairing the steering committee, and of course to everyone who submitted papers. I thought we should also just take a very quick moment to congratulate Cynthia on recently winning the Keynote Prize, along with all the other prizes she's won before. As most of you know, Cynthia has fantastic seminal work in cryptography, privacy, and fairness, all very relevant to this conference. And her award further notes that FORC has played a remarkable role in mentoring young researchers and nurturing their talent. We really hope that that spirit will be very much present in this new conference. We have a host of excellent technical talks coming up. I'll try to keep this a little bit lighter while still addressing fundamental issues we care deeply about. The work I'm going to present is joint work with great colleagues that's showing the bottom of the screen here. Some people I know have moved institution, but I'm showing the institutions that they were at when we did the work. I particularly want to thank the people I'm showing in blue here. It's Nina, Krishna, Till, and Bilal, all of whom have kindly contributed slides that I'm going to use in this talk. So today I'd like to present a selection of some of our results on fairness and machine learning from the last couple of years. Specifically, I'll show ways we might want to go beyond typically discussed measures of group statistical parity. The context will be familiar. We're seeing increasing deployment of algorithms in many important settings which directly affect human lives. There's hope that this might lead to greater accuracy, efficiency, and consistency. But a big concern is to be sure that people will be treated fairly. For example, when helping to decide whether or not to make a bank loan, or when screening candidates to hire, and perhaps even more so in criminal justice. Machine learning systems we develop and deploy should treat all people fairly. Now, this has led to rapidly growing interest in fairness in machine learning. Many of you have probably seen this slide from a few years ago that I think is from Moritz Hart. It's a cartoon illustration of a partial history of what's been going on. As you can see, there was little attention until a few years ago, but since then, happily, interest has grown quickly. And actually, some of you may know, where you can see O on the right here, there used to be an expletive after that, but I removed that for this talk. Yet it's still early days. We're trying to figure out what we really need to make progress on fairness. In our technical community, we like precise definitions. But what does fairness really mean? Of course, this has been debated for millennia by philosophers, by politicians, and by almost all of us. In fact, one of the people that's been debating it is the set of, this chap who is an expert FBI negotiator, Chris Voss. He's pretty slick, and for some reason, when I was working on this presentation, I've been getting lots of pop-ups of this guy in my Facebook feed advertising his masterclass. Anyway, let's see what he has to say. I hope this is working.
The F word in negotiations is fair. Fair is the F-bomb. And when you begin to look for it, it's stunning in how many negotiations somebody drops the F-bomb in the negotiation.
Okay, so we humans care deeply about that four-letter F word, the F-bomb. And one common answer to what fairness means is that it relates to equality. But equality of what? In fact, that was the title of an essay by Amartya Sen, a famous Nobel Prize-winning economist. And most work in machine learning fairness has embraced notions of group fairness. That is, we look for equality of something across groups, where those groups are determined by sensitive features, such as gender or race. And here I'm showing at the bottom here a whole load of legally recognized protected classes. Still, what is that something which we want to hold equal? Well, two widely used ideas are inspired by anti-discrimination legislation. One is parity in treatment, but the focus is on the treatment or the process. We'll come back to that idea later in this talk. The second is parity in impact. This is outcome-oriented. Each group, for example, men and women, should receive a similar fraction of something. And that fraction could, for example, be the beneficial outcome. If a bank is deciding whether or not a customer will repay a loan, then it could be beneficial outcome is that you predict that the loan will be repaid. Now, this idea that each group should statistically receive a similar fraction of benefits is just one of a range of group statistical approaches which are typically taken. What I've just described is sometimes called demographic parity. Demographic parity doesn't take account of important information like credit worthiness. There are a variety of other common measures. Two others are equality of opportunity, which explicitly does take into account credit worthiness. That is, we only look at those who will repay, and of those, we require that men and women should get the same acceptance rates. Sometimes we describe that as having equal true positive rate. Or equal accuracy, where we require that predictions should be equally accurate for men and for women. And there are a whole host of other different measures. And typically we allow small tolerance in how we enforce these measures. We're going to explore whether, in fact, even with that, aiming for parity perhaps is too restrictive. Can we do better than that in a principled way? And as I examine that, we're going to examine parity and impact, focusing on demographic parity for ease of illustration. So here is a headline in the New York Times not long ago. Black people are charged at a higher rate than whites. What if prosecutors didn't know their race? This illustrates the idea of treatment parity. Indeed, perhaps it would be good if prosecutors couldn't even see the sensitive attribute. This can sound good. The one problem, of course, is we might be able to infer the sensitive attribute from other features. But let me point out another problem. In some areas, historically, blacks were charged by police more than whites, even if they acted in the same way. And one of the applications we'll be looking at is estimating the chance that someone will commit a crime in the future. Their prior arrests and convictions can be important features in making the prediction. Now, if overall blacks tend to be charged more often than whites, then what happens when we predict future crime? Well, we'll overpredict blacks' future crime. So in order to adjust for the past bias, it would make sense to use a different prediction function for blacks and whites. In this case, it would seem perhaps more fair to do that. However, we've seen a lot of resistance to the idea of using different prediction functions for different groups. It can look like we're lowering the bar, or using affirmative action, or reverse discrimination. So here I'm going to make a principal case for using different prediction functions for different groups based on ideas from economics. I should mention that we weren't the only ones thinking about this. There's related good work, including by Cynthia, by Zach Limpton, Alex Koldakova, and others. The idea is that we're going to move beyond parity and explore preference-based notions of fairness. These are inspired by notions of envy-free fair division. Envy-free cake division goes back to ideas introduced by Gamow and Stern in the 50s. The essential idea is that each participant is happier with their allocation than if they switched. So no party feels any envy for the other's allocation. We're also going to look at issues of fair resource allocation, which were looked at in economics by Foley back in the 60s. The essential thing we're going to look at is notions of group envy-freeness. They're going to give us a justified way to use different classifiers for different groups, provided that each group prefers their own respective outcome. And we'll see that this can lead to significant gains in overall accuracy. So this is the base idea of parity in treatment, which requires that we cannot use the sensitive feature. We must use just one classifier, which may seem overly restrictive. So here's an illustrative, very simple example. Here, everyone has two features, as shown on the X and the Y axes. We're going to be showing men with an M in purple and women in blue with a W. The green areas show true positives, and the red areas show true negatives. And notice that the feature distributions are quite different for men and women. The x-axis is highly predictive for women, and the y-axis is highly predictive for men. We're going to assume that points are uniformly distributed within each square, and for simplicity, we'll consider the class of linear classifier boundaries. So here is what you get for parity treatment, where everyone gets the same classifier, and we're aiming for maximum overall accuracy. You can see that the most accurate single linear decision boundary, shown here, has accuracy of 83%. In fact, it gets all the women correct. But the classifier gives all men the negative class, which misclassifies 100 men, and it's not really clear if that's fair. So now let's consider our new group envy-free notion of preferred treatment. Here the idea is that we're going to be able to use two classifiers. For each group, we optimize its own classifier for accuracy. And what we require is that no group would prefer to pose as another group to get the other group's classifier. So let's see how that looks on the right here. So the solution here is now using two classifiers, one for each group. And you can see it has much higher accuracy. In fact, it went from 83% to 100%. And as well as high accuracy, notice that men don't want the boundary for women and vice versa. So just to make that clearer, if the men use the men's classifier, then 1/3 of them get the benefit. If the men use the women's classifier, none of them would get benefits. And similarly for women, when the women use the women's classifier, 2/3 of them get benefits. If the women use the men's classifier, none of them would get benefits. So neither of them has an incentive to change group, and we hope that that avoids the potential claim of reverse discrimination of lowering the bar. And note we've gained significantly higher accuracy. So just to clarify, preferred treatment is a strict relaxation of parity treatment, and it will enable us to get higher accuracy. In both cases, we optimize for accuracy, but we hear it's a relaxed constraint. So now let's go from treatment to impact. If we want a single linear classifier to have parity impact, that is, we want to require that both groups get the same benefit, then we must lose some accuracy compared to the earlier single classifier solution, which didn't have the constraint. And we get the solution shown here. Notice that the accuracy dropped from 83% to 72%, and now we've got the same benefit for men and women, which is what we required for parity impact. So our new notion of preferred impact is inspired by the idea of a bargaining solution, where we optimize for accuracy with two classifiers, and preferred impact enables more benefits to all the groups. Each group is going to get at least as much benefit as they did before with parity impact. So in this case, here we get the solution shown on the right with two classifiers. Both groups are better off than they were with the previous parity impact classifier. And in fact, in this case, the preferred impact classifiers are exactly the same as the preferred treatment classifiers, but that won't always be the case. As before, preferred impact is a strict relaxation of parity impact, which will enable greater accuracy and benefits. I should just note that the optimization for our preferred notions is implemented by minimizing a convex loss term and a ramp relaxation of the benefits, which then enable us to use a recent approach called disciplined convex concave programming by Stephen Boyd and others from 2016. That gives us a heuristic to find a good solution. So let's see how that looks on the ProPublica Compass dataset. This is probably familiar to all of you, but I'm going to use this as a running example. So let me just explain quickly what it is. As many of you probably know, Compass is a proprietary recidivism prediction tool. It was developed by Equivant. It was formerly called Northpoint. What it does is it predicts whether an individual will commit a crime within 2 years. It's proprietary, but ProPublica helpfully gathered data from Broward County in Florida across 2013 to 14, and that gathered the actual Compass prediction, along with features such as the number of prior criminal offenses, arrest charge description, juvenile misdemeanors, age, gender, and race. We're going to use here a data set with the characteristics shown here. We're considering blacks and whites, and here yes means the good outcome, which actually means a negative prediction for crime. So yes means, yes, we do not predict that you will commit a crime in the future. So let me talk you through the results here to try and explain what's going on. We have class 0 shown in red, which are the blacks, and class 1 shown in blue, which are the whites. So you just think of the reds and blues as the two different colors. We always optimize for accuracy with various constraint options. So on the left, we're showing the unconstrained setting with 2 classifiers, where each classifier, one for each group, optimizes for accuracy just on its own group. Here we get the best accuracy, but we don't satisfy preferred treatment or preferred impact. And let's just make sure you can see that. The accuracy is in gray with the scale on the right. So you see the unconstrained has the highest accuracy. The benefits are shown by colors on the left. There's a solid bar if the class is using its own classifier, and a hatched bar that shows what happens if we switch to the other classifier. So for the unconstrained setting, notice that the red hatched bar is significantly higher than the red solid bar, so this is not preferred treatment, if that makes sense. Let's look next at the parity of treatment and impact. Here we have one classifier trained to maximize overall accuracy with approximately equal benefits across the groups with a little tolerance. And note that we have a very large drop in accuracy in order to achieve this parity. So now let's look at preferred treatment. Here we're using 2 classifiers. Each group gets more benefit with its classifier than it does with the other one, subject to a bit of tolerance. That is, the solid bar is at least as high as the hatchet, with a little tolerance. I notice that we achieve much higher accuracy. In fact, we get accuracy that's almost as high as the unconstrained setting. For preferred impact, if we compare that to the parity setting, we achieve benefits that are at least as high for each group with significant accuracy gains. We don't achieve preferred treatment because if you look at the blue group, you see that the solid bar is beneath the hatchet bar. And preferred both achieves both preferred treatment and preferred impact. Compared to the parity solution, we get gains in accuracy and benefits. I know we went over that a bit quickly. Of course, please look at the paper if you're interested in that. So let me just recap. We've introduced 2 preference-based notions of fairness. With preferred treatment, each group prefers their own classifier to switching to the other groups. And preferred impact, each group prefers the outcomes that they get with that over the parity impact solution. They get higher benefits. And preference-based notions can lead to more accurate solutions. Okay, but there are still problems. For example, how should we think about fairness when groups are of very different sizes? How should we weight unfairness for each of those groups? And while we've talked about ideas of group fairness, what about what happens within a group? Here I've borrowed a slide from Aaron. Imagine we have this setting. We've got blue and green people, and we have males and females, and they're accepted individuals who are getting the good outcome. So here, if we split the population into male and female, if you look at accepted individuals, it appears fair. Similarly, if we split by blue versus green people. But clearly, overall, this doesn't look fair. For example, green males and blue females get no benefits at all. So one approach here would be to add more sensitive groups or to consider all the intersections. There's good work here by Aaron, by Michael Kearns and others. But instead, I'll propose something which is arguably in some ways a bit more general. We're going to combine ideas of group fairness with notions of individual fairness. That is, we're going to propose a measure which captures both between and within group fairness and measures to what extent each individual is getting what they deserve. So next I'm going to talk about a principled way to achieve that, again, drawing on inspiration from economics. So the idea is that we're going to suggest that we should measure unfairness using inequality indices. This is going to give us a principled measure of unfairness by adapting a measure from economics to algorithmic decision making. We're going to satisfy certain desirable fairness properties or axioms and know that these are adaptable to different types of unfairness. And just before I go on, let me just note that some of you may be familiar with a similar approach that people have been pursuing fruitfully in interpretability. So there's been interesting progress where people have tried to specify certain properties, which are sometimes also called axioms, of feature attribution scores, which are helpful in feature attribution methods. And it can be shown that if you want to satisfy certain very reasonable sounding properties, then you need to use something called the Shapley value. So this is a similar kind of idea. And by doing this, we're going to reveal relationships between individual and group fairness. So let me briefly tell you about the idea of inequality indices. The idea is that you want to have something which measures how unequal different members are of a particular set or different group. There are many different inequality indices. Probably the one that most people might have heard about is called the Gini index, as defined on the top. And there's a chart at the bottom here. This shows the Gini coefficient for UK income levels. The lower the number, the less unequal different incomes have been. So perhaps surprisingly, actually over this period, 1990 to 2017, overall income levels were becoming a little bit less unequal. They've moved around quite a bit. And we're going to be particularly interested in something called generalized entropy indices, which have also been discussed for a while in economics. They have certain very desirable properties we'll talk about in a second. You'll notice that there's this parameter alpha, and that parameter represents the weight given to distances between incomes at different parts of the income distribution. You can take any real value. For lower values of alpha, the index is more sensitive to changes in the lower tail of the distribution. And for higher values, it's more sensitive to changes that affect the upper tail. And here we're going to use a commonly used value of 2. So here are some desirable properties for inequality indices, and I claim also for an unfairness measure, where we're going to use and reinterpret income here to mean the benefit, which we'll look at in the unfairness measure. So zero normalization means that we want to have zero inequality, zero unfairness, if everyone gets the same income, same benefit. Anonymity means that the inequality will be independent of the identity of the different individuals. Scale invariance means that for any constant C, if you scale up all of the incomes, benefits by some constant C, it doesn't change the inequality level. And population invariance, what this figure is trying to indicate is that if you were to just duplicate the population any number of times, then that wouldn't change the measure. The transfer principle says that if you want to be sure that when you transfer income from a high to a low earning individual, that will decrease inequality. So those all make good sense. And actually, the Gini index satisfies all of those properties. But what it doesn't satisfy is the next property, which is very desirable for us, which is this property of being subgroup decomposable. So this is the idea that for any partition of the population into different subgroups, we'd like the total inequality to be the sum of intergroup inequality, where we assign each person in the group the mean for the group, together with a weighted sum of intra-group inequalities. And it turns out that actually, subject to mild conditions, the generalized entropy indices that I defined on the previous slide, they're the only indices which will satisfy all of these axioms. So they suit us very well. That was shown by Shorrocks in 1980. And I just briefly also note that there's a lot of flexibility here in how we define the benefit, which is going to replace income. And by doing that in different ways, we can mimic various popular group notions of fairness. For example, we could have a benefit of 1 for a true positive, otherwise 0, and that would give us something very similar to equal accuracy. But what I'm going to do next is I'm going to take benefit to be an idea of undeserved benefit. So it's going to be the difference in predicted versus actual outcome, where we'll normalize it with an adjustment to make sure that it's non-negative. So you get 1 with an accurate prediction, 2 with a false positive, because you're getting kind of an undeserved benefit, or 0 with a false negative. And let's see what we get when we apply this inequality index idea, again, to that ProPublica compass data set. So here we are on the left showing what happens when you vary the covariance threshold, where the covariance threshold is a knob to control the acceptable level of group unfairness using a previous method. It's a method which bounds the covariance between misclassification distance from the decision boundary and the sensitive feature value. So a value of 1 on the covariance threshold means no fairness constraints are applied. And as we dial it to the right at 0, it means the tightest possible constraints. What you can see is as you do that, it does bring down the between group unfairness. But if you look in the middle, you'll see that actually the within group unfairness is, for most of that, it's actually increasing for whites. And if you look at the total unfairness, which is shown on the right, it's moving around quite unpredictably. And you can see that eliminating between group unfairness can actually end up increasing within group unfairness. And it can even lead to overall increased individual unfairness. So just summarizing where we are here, we've introduced inequality indices as a flexible principal measure of algorithmic unfairness, providing a unified approach to measure both between and within group unfairness. Okay, let's think back now to the F word, the F bomb, fairness. And recall that I mentioned the two ways of thinking about fairness. There's outcome fairness, which we've just been discussing, and process fairness. So now we're going to look at ways where we might try to understand and account for human perceptions of fairness in algorithm-supported decision-making. We'll again look at the compass tool, and whereas before we were looking at whether the outcome is fair, we're now going to try to ask the question about whether it's fair to use specific features. Actually, we're going to look at three questions. We're going to try to address the question of which features do people perceive as being fair to use. We're going to ask, how might we try to account for people's fairness perceptions? And we're going to start to just explore a little bit, why do people perceive certain features as being unfair? So the way we're going to do that, we're going to answer the first two questions. Actually, is it's going to be quite straightforward. Sorry. The way we're going to find out if a feature is fair is we're just going to ask people. So we're going to determine the fairness or unfairness of a particular feature by just looking at the fraction of people that consider using the feature to be fair. And if we're interested in the fairness of using a set of features, we'll look at the fraction of people that consider all those features to be fair. And defining fairness of a set in this way is clearly one straightforward way to do it, and it has a desirable property, which is that if we naturally define unfairness to be 1 minus fairness, 1 minus that fairness fraction, then as we consider different subsets of features, unfairness is submodular and monotone non-decreasing. That is, as we add more features to those that we might use for a classifier, intuitively, the unfairness will go up and with diminishing returns. So to do this, we asked 200 AMT master workers, and I recognize that there are potential issues with doing that, but it was a preliminary investigation. And let me just talk to you quickly through some of the results that we saw. So we've got the different features shown on the x-axis, and for each of these features, we're showing how people responded, to is this feature fair or not to use for predicting whether someone is going to commit a crime in the next 2 years. We're actually on the left, we actually asked three different questions. There's the a priori judgment, which is shown in the green squares. That is, we just asked that question, is it fair to use that feature? Then we also asked some interesting other questions. We said, well, what if using that feature will significantly improve prediction accuracy? And that's the yellow circles on the left marked with AC for accuracy. We also asked, what if it increases disparity? That is, we said, what if there's a chance that some subgroup will be falsely predicted as having a higher risk than others? And that's the diffs number shown in blue. So actually that brought the numbers down. So overall, you can see that some interesting patterns there are, that there were quite different notions of fairness that people attributed to different features. The three on the left are perhaps directly related to whether someone is likely to commit a crime. And they're also arguably volitional. That is, arguably that they're more under the control of the individual, some of the other parameters. And then we know that the people's ideas about fairness starts to come down as things get increasingly distantly related. I thought I'd also show you these interesting results on the right. So if you split the respondents by those who self-report as having a conservative or a liberal political leaning, first, conservatives tend to find it more fair to use all the different features. And particularly if it's known that the feature will increase disparity, you can see that that doesn't change conservatives' views very much, whereas it changes liberals' views quite a lot. So that's interesting. Perhaps it's not surprising. It may link to ideas about moral foundations theory, that perhaps conservatives are less sensitive in general to this notion about features potentially influencing some groups more than others. So I'll leave that aside for now. So now let's talk about how we can actually try to account for these fairness judgments, if we want to try to optimize subjects to these judgments. So our goal is to train a machine learning algorithm that will achieve high accuracy, subject to a constraint that unfairness is going to be less than some threshold. The intuition is that as we add features to what the classifier can use, we'll get higher accuracy, but lower fairness. So there's a trade-off between perceived fairness of features and the accuracy. Let's see how that works out. As I pointed out before, with our definition, the notion of unfairness is actually submodular and monotone increasing. It also turns out for the classifier we used, which was logistic regression with LT regularization, accuracy is weakly submodular. And so we are able to use a result by Iyer and Byams from New York 2013, uses iterated submodular cost knapsack approximate solution to let us change the unfairness threshold and observe the accuracy. In fact, for this problem, the number of features was sufficiently small that we're plotting the exact solution with the green squares and the approximate solution with the algorithm with the yellow circles. You can see there's almost exact agreement, which is promising for scaling up to larger sets. And you can see that this does enable us to operationalize this idea. And what we've marked on this chart might be interesting. When the unfairness threshold is 0, you're not allowed to use any features, and just the constant classifier is 55% accurate. And then as you increase the unfairness threshold, additional features start popping in, and you can see when other particular features come in and allow us to increase accuracy. Okay, so at this stage, we felt we really wanted to delve a bit further into our other question, which is why do people perceive some features as unfair? So we did a deeper dive on the COMPASS questionnaire itself, focusing on bail decisions. So the actual COMPASS questionnaire has 137 questions, which are divided among 10 different topics. There are the topics shown here. And just an example for criminal attitudes, one of the questions is, do you think that a hungry person has a right to steal? Or for criminal history of friends and family, you asked, how many of your friends have ever been arrested? Notice there were no questions about sensitive features, interestingly. And what we asked people was, is it fair to use these features in order to make bail decisions? We looked at, again, at Amazon Mechanical Turk master workers. We also used this other panel, which was a bit more representative of demographics in the US, and our findings were consistent across both samples. Let me just give you some of the highlights. The first thing to notice is that, actually, quite interestingly, people considered most of the features to be unfair. So this is the y-axis is a Likert scale. At the top shows people thought a feature was very fair, and at the bottom it means they thought it was very unfair. You can see there are only two kinds of features that people thought were significantly fair. Now we're going to keep the same order of these on the x-axis, and let's see, to ask the question: do people agree in their fairness judgments? And it turns out that they tend to agree on the two features considered most fair, but otherwise there's a lot of disagreement. So we wanted to ask, why do people disagree? And we had a hypothesis. We hypothesized that perhaps people determine if it's fair to use a feature based on certain underlying properties of the feature. So it could be that people disagree about the latent properties of each feature. We came up with these particular properties. They're based on ideas from law and literature and social economic, political and moral science. You might not think they're the perfect ones. We can discuss that, debate it later, but it was interesting. I'll show you why the results are quite interesting and why we thought that these actually maybe did make good sense. We wanted to explore these, and don't have too much time, so I'll just go over this pretty quickly. I'll point out, though, that the first two, relevance and reliability, are actually requirements for evidence to be admitted into a court of law, and the other ones also have some good justification. So we asked people what makes a feature fair or unfair to use. We gave them these 8 options and also another option, and actually each of the explanations we gave, each of the latent properties, received at least 15% of the fairness judgments, which made us feel good, and only 3% of people ticked the other box. So we felt there was reasonable coverage. And what we thought is that perhaps people actually decide if it's fair to use a feature by weighing these latent properties of a feature in a certain way. So explanation 2 for why there's disagreement about fairness, well, remind you, explanation 1 might be that people come up with different latent properties. Explanation 2 could be that people disagree about the mapping from latent features to fairness. So what would you expect? Would you expect that people disagree about the latent properties that a feature has? Or do you expect that people would disagree about the mapping from latent properties to fairness? So we had thought that the latent properties would be relatively objective, whereas the mappings to fairness could vary a lot. But it turned out, at least in this case, that the results were the other way around. So that there was significant disagreement in coming up in the latent property assessments, particularly for the issues around causality, which is interesting because many of you may know there's a very interesting body of work that tries to look at fairness from a perspective of causality. And there, you typically need to know what the causal structure is, but this seems to indicate that there's a lot of potential disagreement about the causal structure. And then we actually observed that if we knew the latent properties, then we could predict people's fairness judgments with very high accuracy. That is, we were able to model a common fairness judgment heuristic, which for almost everyone gave high accuracy for telling us about their fairness judgments about particular features. So let me just summarize this piece of work. At least on this data set, the fairness of using a feature, or people's views of fairness of using a feature, depends on the latent properties. We also notice that fairness considerations go beyond discrimination. These ideas of relevance, whether a property is volitional, whether it's reliable, whether it's private. And there's significant disagreement in fairness judgments. At least here, though, interestingly, there seems to be agreement in mapping from latent properties to fairness, but a disagreement in those latent properties, especially those related to causality. So this suggests it would be interesting in future work to look across cultural studies of human perceptions of fairness. Just starting to wrap up, let me talk about something I think is very important to look at perhaps next. I know some people in the community are already starting to think about, but I think it's very important. And if people are interested, I'd be delighted to try to collaborate on this. So I think we want to be careful not to focus myopically just on the algorithm, but think about fairness of the whole decision process. So here's a headline from the Washington Post late last year. Algorithms were supposed to make Virginia judges fairer. But what happened was far more complicated. This is reporting on a paper by Megan Stevenson and Jennifer Doleac. What happened is they observed that when algorithmic indicators were shown to judges, advising them on the chance of people committing a crime in the future, you got quite unpredictable effects. And in fact, racial disparities increased among circuits with judges that used risk assessment tools the most.
Adrian, sorry to interrupt. Just want to let you know that we've got a bunch of questions already, and so with 10 minutes left, if you're able to, steer us towards the end, we'd love to be able to ask you a bunch of questions.
Absolutely, thanks, Raj. I'll take just about another 40 seconds. So I think this is a really important area. How can we help users understand what algorithms are telling them in order to get better outcomes overall? There's a lot to explore here. Overall, I'd say that as a community, we still have a lot of important work to do. If people are interested in these questions, please get in touch with me. We need technical expertise, but we also have a lot to learn from social scientists, lawyers, philosophers, policymakers, and real-world practitioners. We should engage with them and together try to make a positive impact on society. Thank you.
Well, thank you very much, Adrian, for this talk. It's a lot of things. I have a whole bunch of my own questions written down. I'll defer to the audience. You have a bunch of questions to the audience, and just as a reminder, if you would like to ask Adrian a question, please post in the Q&A, and I will read out the question. I hope to get as many questions as I can. And without further ado, let me do that first. And so for various technical reasons, if you're following the Q&A, there's some questions that didn't get posted there, but I'm going to read off from other sources as well. So the first question comes from Alani Cohen, who asks, in the preferred impact example, this is early in your talk, every individual is no worse off in terms of received benefits with a groups classifier. But what if some individuals fare better under the groups classifier, but not the group as a whole?
That's a great question. Indeed, the notion which I presented was really a notion of group preference. So as a whole, the group would prefer the classifier or prefer the outcome, but that doesn't necessarily mean in that treatment that every individual in the group would necessarily prefer it. Now you could, in fact, conceptually, apply the same types of constraint for every single individual, but of course that's tricky because how do you even define some of these notions at the individual level? That becomes hard, and you also start to get a tremendous number of constraints then, which makes it computationally challenging. But just clarifying, yes, the notion I presented was for the group, and wouldn't, if you did just what I said there, you wouldn't necessarily get a better outcome for each individual.
Thanks. The next question is in the Q&A from Ben. Does the idea of using a different classifier for each group have any relation to the game theory idea of the core? For example, no class prefers to have the other classifier, but could some subset of the class prefer to have a different classifier? This feels a bit similar to the previous one, but also different.
So I apologize, I forget exactly how a core is defined. I know it should be on top of it. So I'm afraid I'm going to pass on that for now, but I'd be happy to look at it together afterwards and discuss.
Okay. The next question, sorry, was there someone trying to, so the next question is from Michael Yang. If the original data are biased, for example, Black Americans are more likely to be arrested and convicted for similar crimes, what is the importance of individual fairness, i.e. treating individuals as similar based on the biased input features as factual?
Well, I think, I'm not sure I've understood the question. I think it's, I think that these are sort of basic notions about fairness, which you can debate, and different people may have strong views about. But certain people feel very strongly about group fairness, and that's obviously that's often based on issues of past discrimination at a group level and legal notions of legal recourse built around that. But also many people think that we need to be very mindful of individual fairness for its own sake, that it just makes sense that we need to treat each person appropriately individually. And I'm not sure I've understood why it makes a difference whether the original data is biased or not when you think about that. Can you help me understand?
So at the risk of trying to interpret the questioner, I think maybe the implication is that, is there a way in which different notions of fairness, and maybe individual is one of them, are more or less sensitive to biases in the input data, because we are, after all, relying on the representation of the input to define a notion of similarity. And I think this goes back to the other broader discussions about the metric and how you define similarity in the case of individual fairness.
Good, good. So I hope I'm catching the right thing here. So clearly an important issue. Let's pick let's pick a particular racial class. So in many situations, historically, Blacks have been discriminated against, have been worse off in various countries, and we need to try to fix that. But of course, on an individual basis, it's true that certain of those Blacks actually have been, may have had a privileged background. In fact, maybe more privileged than certain whites or people of a different color. And if we totally ignore that, many people might consider that not to be fair. And so we do want to try to figure out how we can address that. And if we want to be able to do that by looking at the data, we're going to need some more fine-grained variables, some more fine-grained way to analyze where the discrimination is coming from. Potentially causal analysis could help there, but certainly we will need to gather more information. I hope that's answering that a bit better.
So Michael certified that my reinterpretation was not totally inaccurate. So that's okay. So a question comes from Omer Reingold. How can we prevent abuse of the definition by the male classifier for men rejecting all women artificially and vice versa? Because if you allow this to happen, then no matter what the classifiers do on the intended group, it'll look like there's no envy. But I think Omer's point is that this is not a desired outcome. So how do you prevent that abuse of the system?
Well, maybe I didn't explain it well, or maybe I misunderstood the question, but using the preferred notion, it can't be that males can choose a classifier for the women and then reject all the women. The males can get the benefit of the male classifier, but the women get the benefit of the women classifier, which is optimized for the women. So it's not under the men's control, or did I misunderstand?
I'll let Omer sort of maybe write in clarification if necessary. In the meantime, I'll move on to the next question just because of time. One question by Charles Cree is, do you think there's often a discrepancy between what people perceive to be fair and the more objective or mathematical measures of fairness that researchers use? And if so, how do we pick which to use?
That's a great question. I think the answer is clearly yes. And it's not because people's perceptions are wrong and our clean, pure technical descriptions are right. I'd say we're just at the very beginning of really trying to address these topics. Well, we're not. Mankind has been trying to address these topics for a very long time. There's a recent, very welcome uptick in our technical community trying to embrace these ideas. But the way that we know how to address these kinds of topics is to try to express notions of fairness in these very clear, specific constraint terms. Now, clearly that doesn't encapsulate all of the issues which we as humans feel are very important in terms of fairness. And we're going to need over time to do a much better job of doing that. In fact, sometimes I think we are even ridiculed by ethicists and lawyers for such kind of caricatures of notions of fairness. But I think we should welcome that, and we need to keep engaging. I think we're starting to help to sharpen the pencil about thinking about what we do really want. In many settings, these notions are going to be woefully inadequate, and there we need to understand better what is needed and try to figure out how we can better work with people to do a better job in combination. Certainly our algorithmic systems are no good at all at having ideas of common sense or general knowledge, but we can try to work towards that. But in the meantime, we can note that humans are much better at those things, whereas actually algorithmic systems are much better at some other things like consistency and precision and finding patterns across lots of data. So there are some settings where one makes more sense than the other, but in general, I think we want to try to get both humans and machines to work well together across different settings.
Thanks. Given the time, I'm going to just go for one more question, and I'm going to just jump a bit. Apologies for jumping ahead. But this question I think is interesting. Zainab asks, what do you say about the dynamic nature of fairness, for example, over time, demographics, and culture? How do you think about that? And that'll be the last question.
I think that's a fascinating area. I think many of us were really excited when Moritz Hart and others, sorry, I forget all the co-authors, who got the best paper prize at ICML recently for that paper on a dynamic notion of fairness. I think it's really important. Clearly, just as I've mentioned, you could say that some of our rigid constraint notions of fairness are kind of caricatures. You could say it's also a caricature to say that it should just be imposed statically at one particular time point. Clearly, what matters is what happens over time. And I think it's very welcome that people are starting to look at how these notions of fairness will propagate out. So for example, this is starting to be looked at under titles like strategic classification, where again, a lot of interesting work, and I think this links in with economics, and we could fruitfully try to collaborate together. So things like, it's well known that if you publish an algorithm that you're using to make some important decision, like who you're going to admit into a university, if you're going to say you're going to use SAT scores, then people will certainly try to train to that test to do better on the test. And that may then mean that the measure you initially used may become less good at measuring what you wanted it to measure. That's Goodhart's law. So when you tell people what kinds of things you're going to measure, they will react to that, and you may react to that in a kind of cycle. And it's very interesting that people are starting to look at that and try to figure out how causality plays into that and how you might optimally want to tell people certain things that you want them to try to change, but maybe not tell them about other things that you wouldn't want them to change. So this, I think, plays very interestingly into the intersection of economics and interpretability and transparency and fairness. And I think there's a lot of interesting work to do there. Great question.
All right.
All right.
And
oh, sorry, Aaron, there was a question from the audience about recording and talk slides. So I'll let you answer that and also conclude the session.
Sure. Yeah, the whole session's being recorded, and everything should be made available afterwards.